University of Kent, telling us about Erlang on Toast, a toolchain for generating correct by construction Erlang programs.
Thank you for being here. I'm sorry for the technical problems. Okay, so yeah, I'm going to talk about today Erlang on Toast, which is a under development toolchain. But first, I just need to get it out of the way. What are Toast? Toast stands for timeout asynchronous session types. And we are going to be using these throughout this. And these are a theoretical formal model. And we use these to generate our stubs. The sort of programs that we're going to generate are intended for the concurrent and distributed setting, which is why we chose Erlang. And we will be generating our correct by construction stubs from Toast protocols, which are a formally grounded model, which are able to enjoy all sorts of nice and helpful properties, but it's quite difficult to bridge the gap between the theory and the actual real-world implementations. Toast are a derivative of asynchronous and time session types, and we are going to be focusing on the binary setting, where in these concurrent and distributed systems, there'll be processes communicating together, but we'll only be focusing when there's two, and these are the binary sessions. The motivations behind this work are, there's several. To begin, in large-scale distributed systems, it is quite common for them to be unable to be statically verified. And in these instances, it is often more advantageous to assume and preempt the failure to then focus on the recovery. This is in part due to the lack of expressiveness of existing formal models that are unable to capture the behavior present in real systems. For example, timeouts. Aside from the verification of existing systems, it can be difficult to implement protocols from their specification because they're often quite abstract and they aren't very language specific. And it can be, the person implementing them is just, it could just be a normal programmer. They might not have much of an understanding of the way that protocols are designed and the meaning behind them. And this is especially true when we're talking about timed protocols. And all of this together, there's a new potential in Toast because they are both able to model timeouts, and we are then developing this tool to help bridge the gap with all of these areas. This is, again, a very work in progress early draft of our toolchain. So in this tool, I'm going to go over a typical workflow of how you may use our tool, and the different stages that occur both internally and externally by the user. I'm then going to cover some of the more theoretical components, before then introducing our working example, where we will then explore how we may implement this in Erlang. And then I will discuss runtime monitors, because our tool features a template which is quite unique and interesting. We will explore that later. And then we will finish with the demo, which is a culmination of the previous examples, but showing the actual code generated by our toolchain and the different ways that it may terminate, because we're interested here in ensuring that the behavior adheres to the formal model, correct by construction. And then I'll outline some future work. So to begin, to use our toolchain, the user would first have to have some kind of protocol, a formally grounded one in Toast. And then the next step would be to derive some kind of either Toast process, which is based on the process calculus, and that corresponds to Toast, or we have another notation for this tool, which is the Erlang API. And either of these may be used for our tool, as we have a mapping between them. And this can then be used, got ahead of myself. The main assumption is that either the Toast process or the Erlang API must be well typed against some well-formed Toast protocol. And this is the foundation for our work. Given either of the Toast process or the Erlang API, the user can then use it as input to our tool. Our tool will then generate an internal finite state machine to model the behavior of the input, and then it would generate an Erlang stub. These stubs also contain a runtime monitor specification, which can be used by our runtime monitoring template included with our tool. Given that we only generate Erlang stubs, the user will still need to extend it with the functionality. Our stubs specifically only specify the interaction structure, but the actual main matter of what you're sending is up to the user, and this is where, extend functionality. Then, when the user may run the program at runtime, the programs can be configured to automatically start themselves with a runtime monitor that uses the spec provided when the tool generates the stuff. These can be configured to be for verification against the Toast protocol they were generated from, or to enforce the protocol. And at the end of all this, we hope that this will ensure that you have a well-behaved Erlang process. So now to shift to the theory. What are toasts? I have the syntax here. Not if it's what are timeout asynchronous session types. I overthought this. I went back and forth. So I can talk about this more if people would like, but I'm just going to go over it quickly for now. On the far right, we have N, which is a successful termination type. Then we have new alpha S, which is a recursive definition. Alpha is a recursive call. And then this thing in the brackets, that's a choice type, where you have options ranging over I, where a bang denotes a send action, and a question mark denotes a receiving action. LT would be the message label and payload. And then delta and lambda are time constraints, which I will stray away from discussing too much here. And then S would be the continuation. The important thing about Toast is that they are able to model safe mixed choice and model timeouts. So what are mixed choice? Or what is mixed choice? Here I have a diagram of Ali and Bob. This is a very simple automata diagram where Ali can both send A or receive B. And Bob is the dual of Ali because for every sending action in one, there is a receiving action in the other. Okay. The issue with mixed choice is that it can be problematic because there's nothing to stop here both Ali and Bob from performing their sending actions. And at this point, they may end up in incompatible states. Yes, there are some edge cases where you might be able to receive each other's messages that you sent, but as a general premise, you want every message that you send to be instantly received. That's sort of in the foundational work of these fields. In order for Toast to make mixed choice safe, it ensures that only one of these will be sent. If Ali sends A, then Bob will receive A. And this is what makes it safe. To give a more concrete, to give a more relatable example, if Ali were to be sending a message to Bob via text, they ask Ali out, Bob would then asynchronously receive this, and they may then coincidentally just start typing at the exact same time. And then they both press send, and they asynchronously receive each other's messages, but now they have a completely different view of the world. They've miscommunicated. In here, Ali thinks Bob is a horrible person, and Bob thinks everything's fine. And now, as they proceed, things can't quite be the same. And this is largely just unrecoverable. It's a bad situation. The important thing, in order to make mixed choice safe, is that at any point, only one party can send at any time. You can think of a plain choice is either an internal or an external choice. An internal choice being a selection of various outputs, or an external choice being you're waiting to receive one of a set of branches. But a mixed choice could be both. And we use, I'm not going to show now how Toast makes it safe. If we look at a timeout, we could take Bob, for example. You receive A, you send B. Bob could be a timeout if we specify that you receive A for 3 seconds, then after that, you can send B. This is quite typical of a timeout. And in Erlang, you're able to represent a timeout fairly straightforwardly using the receive after structure, where we would receive A, then after 3 seconds, send B. And it is these timing constraints that make it safe, and this is what Toast provides by using the timing constraints. So by modeling safe mixed choice, we sort of enable modeling of timeouts, and vice versa. But then something interesting happens. So timeouts are a very common interaction pattern. They're found in all sorts of protocols on the web and elsewhere. And primarily, they have been seen as a means to allow a party to disengage if perhaps another process that they are dependent on has maybe gotten stuck or crashed, and it's to stop them from waiting forever. So if we expand on our example before and add the same constraints to Ali as we did Bob, we can see that if Ali does not send A, then Bob should still be able to send B. But under the usual understanding, or I'm saying this now to clarify some things. When I say that Bob sends a timeout, I'm not wanting to say that Ali has got stuck, or has crashed, or has got unlocked. Ali may still very much be alive, and we know this because why else would we specify that Bob could send B to Ali, and why else would Ali even be prepared to receive B? It could just be that Ali is perfectly fine, and this is because when I say a timeout, I'm referring to a mixed choice. I'm referring to a mixed choice where you receive first and then send after. And you can describe with Toast interleaved mixed choice where you may receive and send, receive, send, any manner of these. It could just be that Ali was unable to send A, and that Bob may still send B, and Ali will still receive B in the future. And this is where we get to co-timeouts, because if Bob is a timeout, we say that Ali is a co-timeout. And while it is rather intuitive in Erlang to represent a timeout using a receive after, a co-timeout isn't. There's no such thing as a send after, it's unintuitive, and that's where our example comes in, where we're going to explore this, how you may implement it. So here is a more complex example. It has a client and a server, where the client will produce some data and send it to the server, who is the consumer. The client may send data, and then the server may take some time to process it. If the server detects an error, then it will report it back to the client, and then they'll enter some special state. Otherwise, if the client doesn't receive an error, they may send data, and then send more data, and then as long as they don't receive an error, they can then send stop. And so to summarize, the client can send as many data as they want. This protocol does not put a limit on that. But more subtly, this protocol does not require the server to actually finish processing each data within the second interval. All this protocol requires is that the server remains open to receive the data as they arrive, and this can be achieved by spawning worker processes that help keep the server able to receive and to stop the processing procedure being a blocking kind of behavior. Okay. Hello? Okay. So now we're going to take these examples and look at some very, almost pseudocode Erlang program. They are very similar and based off of the stubs that we generate, but I've had to simplify some things purely for the slides. This one is pretty okay, but the next one, I've taken some liberties. So, if we have the client here, first, we send our data. Then, we straightforwardly if we then receive an error, we handle it, or after a second, we then decide if we should send stop, or then loop background. In order to obtain the server, it's quite easy. Because we're in the binary setting, we can just use duality and flip the signs of each interaction. And when we look at the server now, to begin, I'm going to have to assume that we're already in the loop, just for the sake of space. We could either receive stop, or we could receive data. After receiving data, we spawn our worker function that will process the data and then send the result back to us. Here, we would then receive any data processed, and then if it is an error, we send it and forward it on. If it is not an error, we can then just loop. And then we can wait for the next iteration. The small detail here is that the underscore process ID does not require it to be the most recent one. It could just be any of them. Well, yeah. And then we would receive data and loop. Yes. Okay, cool. So, once our tool has generated the Erlang stubs, the user must extend it with functionality. This is where some problems can arise, because without knowing, they may interfere with the delicate timing interactions. They may sort of ruin the correct by construction property that we're going with. And one way that we can stop this is with runtime monitors. Runtime monitors will ensure that Runtime monitors will ensure that any violations of the protocol are detected and reported to the supervisor. And our monitors are inline, so they are, the process can spawn it within their own node, and they will communicate synchronously, but in an asynchronous session. And these inline monitors are based on our formal model, so they should be sound and complete. And we offer two different monitor presets, as I mentioned before, one being for verification and the other for enforcement. In general, a lot of you may know this, but runtime verification, it doesn't interfere with the communication at all. It only verifies that every message sent or every message received is as described by the spec. Runtime enforcement monitors, however, are quite interesting. The one that we provide could have uses beyond our toolchain, because it would allow completely time-unaware programs to adhere to time-sensitive protocols. This is because an enforcement monitor fully is able to handle the timeliness of an interaction by possibly delaying it until it's ready, but also filtering any incoming or outgoing messages to be only the ones prescribed by the protocol. Yeah, so this is a bit of a demo. I was told QR codes are cool. Don't know if people want QR codes. I can go back. Okay. Here's the server. We're going to focus on the server because it's an interesting thing with a code timeout. We all know how to do timeouts now. So this is how you would represent it using our Erlang API. It's just tuples. And it very closely corresponds to the process calculus in our theory, and we have a mapping between them. Here on line 1, we are set to receive some data. On line 2, we set the recursive definition S1. Line 3, we send error and then enter an error state. But if we can't send error, line 3 and 4 are the send after thing that I described earlier, which don't exist, but we can describe them here, and then our tool will interpret this and build a nice pattern around it, which I'll explore now. So, going through the whole stuff, in practicing this, was not very fun. I had to extend it to make it even interesting. Still very fun. So we're going to go a little snippets, and I'll show you all the different possible outputs for the different configurations. At the top of each of our sub files, we have a header file, and this just contains a bunch of helpful functions that help reduce the visual bloat on our generated stubs, and it would gently stop the user from interfering with things that we need to happen a certain way. So once any generated sub is spawned, it goes via stub start link, which it handles the starting of the monitor if that's necessary. It handles the session instantiation, and then it will enter init. And this is where the user may actually have to interact, because here, if they're being monitored, they can send the parameters to the monitor. Hey, do these sorts of things, like be an enforcement monitor, be a verification monitor, have these different things, like print out or not print out. But after all of this, they then wait for a signal to start from the session. Upon starting, they will then enter a run state, which just points to the main. And here we can see that following the protocol, we will receive data, and then upon receiving our first data, we enter our loop. And loop state 2 describes, on the data we just received, spawn a non-blocking payload is the worker I mentioned. So we spawn a worker that will use a function called getPayload2 to process the data. It'll pass the arguments, the tuple error data. And then, right, yeah, so now we're going to have a look inside getPayload2. By default, it just has an atom, hinting that the user should maybe extend this. And if we extend it, here I've made a simple one where at the top I've defined a macro called error data. If the data received is inside that list, then we say it's an error. So it's a big simplification. So if we return now to the loop, once we've spawned the worker, we wait to see, on line 104, this is where we would wait to receive any message from the worker that we spawned. And if the message that we receive from the worker has the label error, then we know this is an error, and then we will terminate abnormally with this stopping error in processing. Otherwise, if there was no error, or if the processing did not yield an error, then we loop, or we can then, this await payload KO is sort of, inside this function there's another timeout which uses this method here. So after a second, we'll receive KO anyway, and then it will go. And I forgot to include this in the screenshots here, but in the, you can set up your monitor if you're using one. Well, no, yeah, you can set up your stub to make the workers persistent. So by default, this is on to allow the workers to keep existing after the KO. And this is what we're assuming in this case. So even if we do not receive within 1 second, the worker will still be alive. So the next time we enter the loop, we may receive an error from any of the worker process that we started. Okay, so after receiving, if I go back, after receiving either no error or an processing that wasn't an error, we enter the no error body, which is something I've extended this tool with by just shuffling some things around. But here is where we would either receive data and loop again, or stop, and we would stop normally. So if we were to run both the client and the server with monitoring on, here the client has been extended with simple functionality to count from 1 to 10 and just send each integer. The server has been extended to, once it receives number 4, it will find an error in that. And as we can see, and the monitor detects the error, and we can see where it is. If we set the error to not exist, then it will terminate normally. If we stop it, if we turn the monitoring for the server off and have the error be on, then the error will still be detected, this time by the client. If we turn off the monitoring for the client, but turn the monitoring for the server on, as we expect, the error is still detected. Finally, if we turn monitoring off altogether, because we have the terminate abnormally, the error is still detected. So this is good. If I sabotage the stub by having it just send a bunch of errors at the wrong time, and in this instance they're both being monitored, then this is detected, and it gives a special sort of indication of what went wrong. And this is all in the monitoring template. So we have a single monitoring file that you just spawn with different parameters, and it will violate. Look, it will monitor the process you give it against the spec that you give it. Yes, no one, if you do, sorry, because these are just toggleable monitors, the stub and anyone else in the session doesn't have to change at all. It's all handled automatically, because co-party here is just secretly a monitor that redirects as a transparent mediator. But yes, so in future work, if I return to our workflow, there are two areas that we would mainly like to focus on. The first is this first assumption. I listened over it a bit earlier, but it would be quite nice if you could just go straight from the Toast protocol to the input of the tool. This assumption that things are well typed is nice. Like, we have a very, like, version 0.1 of a type checker for Toast, and it works, but it would be nice for the user to not have to design two things. So if we could automatically extract from the protocol itself, that would be ideal. And secondly, we'd like to overhaul our monitors a bit, but also perform a thorough evaluation of them. In the writing of this paper and the development of this work, we just did not have the time or the resources to carry this out. But this would be interesting to explore in the future, like the performance overhead, and maybe make the configuration presets a bit more human readable. So in summary, I have introduced timeout asynchronous session types, or toast, and I've shown how we use them with our toolchain to develop, to generate correct by construction Erlang stubs, and we've explored the behavior of mixed choice, timeouts, and introduced co-timeouts, and tried to connect the dots between the theory and the implementation. Thank you for listening. I'm Jonah, Pears, and Lara was my supervisor, and Raymond, who is our collaborator. Yeah, cool. Thank you.
Thank you. Very interesting talk, which I'm still trying to get my head around most of what you've said. Is it fair to say a lot of this generated code is actually supervisor code?
No, we don't generate any supervisors. I made I've called it gen monitor, but I've then seen that Erlang calls things gen something. So it's just a single monitoring file that I wrote, and then all the rest is generated by a tool.
Okay, and if I'm running distributed Erlang, or whatever it is, I have to have this running in each of the different spaces beforehand. I want all the individual nodes to have the same state of play concept in their head. Is that correct?
So it's designed that you could spawn each stub or process like independently, and as long as they have their own spec, then they'll be monitored. The monitor is completely local, if that answers.
Well, no, but if I'm running my application on multiple different CPUs,
okay,
I still need that instant across the wire on the other side. Well, okay, that's maybe a different. When you're talking about timeouts, I'm a network guy, so I tend to think that you've got a pipe between A and B.
Yes.
Right, and so you might have UDP underneath, you might have TCP underneath, you might have SCTP underneath.
Yes.
You take care of all those timeouts and ignore those failures and just deal with application stuff?
Okay, so you could describe those protocols in Toast, and then yeah, it should just handle it, but this is in development. So Toast is a formal, it's a formal model, it's a session types. Do people know what session types are here? I don't know if I should.
Yeah.
So it's like a way to type the Pi calculus, so that you make a type system. So Toast, like the protocols here, are intended to be based on these formally grounded things. So the specific protocols you mentioned, I feel like yes, you could describe them in Toast maybe. If they have mixed choice, then you can, and that wasn't possible before.
Yeah, I'm probably. You probably could, but they already sort of exist and have underlying properties in the transport of the system. And if they fail, Erlang will already know that they're failing and they failed their way. So the question is, are you hooking into that output as well? Or are you sort of trying to float above it and don't care? or ships in the night? I didn't
Okay.
get that part of the...
Yes, so I've come from the formal thing. So everything you've mentioned, I was not aware of. And that is interesting.
Right,
At this
so,
point,
so we can talk.
I'm floating-
This is very interesting. Right.
I'm floating obliviously on the surface, unaware of the stuff you were mentioning.
The plumbing, right, okay.
Yes.
Sorry, Chris.
Any other questions?
Cool.
Okay, well, thank you, Jonah, for a wonderful talk.
Thank you for waiting.